Assalamualaikum and good morning to the all judges. We are from Group 5C/05, which is study on the hydrogen storage properties and the catalytic mechanism of calcium borohydride CaBH42 composites using TAGUCHI method. Our team members consists of 4 members, which is first is Nur NAQIBAH binti BADDRUN, second Nur ALIYAH SYAFIQAH binti AHAMAD, third AIMAN MASHKUR with MASNU AMIRA, and the fourth SHARIFAH HANNAN binti ABDULLAH.
Alright, first we move to the introduction. Hydrogen has attracted a great deal of attention among researchers as an ideal energy carrier used as a medium for transporting and storing energy. Due to high gravimetric capability and favorable safety consideration, hydrogen storage in a solid-state ship has been one of the alternative methods compared to compressed gas and liquid hydrogen storage. Various materials have been suggested and are currently being studied. As alternative hydrogen storage materials, complex hydrides such as metal halanides and borohydrides are attractive candidates due to their high gravimetric and volumetric hydrogen densities. Like metal borohydrides have great potential as an effective hydrogen storage facility. The relative theoretical hydrogen storage potential of CaBH42 is around 11.6 weight%. However, CaBH42 has drawback in terms of high desorption temperature, sluggish desorption kinetics, and weak reversibility conditions, making it difficult to use them in a hydrogen storage device. A number of studies have been conducted to improve CaBH42's hydrogen storage efficiency, such as doping with different types of catalysts such as TiCl3, NBF5, and TIF3. In this analysis, in order to boost the hydrogen storage properties through a mutual interaction between the two hydrides, the hydrogen storage properties and reaction mechanism of the CaBH42 with various catalysts were investigated.
Assalamualaikum, I am NAQIBAH. Now I will talk about the objective of our final year project. So the first one is to perform the analysis of variant AMIRA of cyanide to noise aspect ratio on onset decomposition temperature, hydrogen release, and activation energy. So the second one is smaller the better as cyanide to noise aspect ratio and optimal condition analysis on onset decomposition temperature. So the third one is the larger the better, cyanide to noise aspect ratio and optimal condition analysis on hydrogen release. And the fourth one is smaller the better, cyanide to noise aspect ratio and optimal condition analysis on activation energy. I will move on to methodology. 100 journals distributed to 4 members, which each member got 25 journals each. So data from 100 journals is collected, being analyzed by the members, and the collected data is being keyed into Excel Google Sheet. So relevant data choose from the data collected or parameter and response will be choose onset decomposition temperature, hydrogen release, and activation energy. So next one is to run TAGUCHI for analysis of variant ANOVA for cyanide to noise aspect ratio of onset decomposition temperature, hydrogen release, and activation energy using Minitab. So the next one is to analyzing the data from TAGUCHI. The last one is the determination of significance of control factors, optimal factors, and levels. So now we talk about the result and the discussion. ANOVA of the aspect ratio on onset decomposition temperature, hydrogen release, and activation energy. So the first one is for onset decomposition temperature. So there is a table. So the P value to be lower than 0.05 to be significant, and the F value is need to be higher than 4 to have a strong impact on the response. We found out that the material and the catalyst is not significant on onset decomposition temperature, and it also has a weak impact on onset decomposition temperature. So for hydrogen release, we found out that the material and the catalyst is significant on hydrogen release, and also has a strong impact on hydrogen release. So for activation energy, we found that once again, material and catalyst is not significant since P value is higher than 0.05. So the material and catalyst also has a great impact on the activation energy since the F value is lower than 4. So that's all from me.
And now we move to the result and discussion of the smaller the better SN ratio and optimum condition analysis on decomposition temperature. In this analysis, SN ratio was used for further explanation, where the smaller the better are the type of analysis that was determined since the lowest value of SN ratio is desirable. In table 3.2.2, the control factors and their SN ratio are summarized. As can be shown, it is clear that the optimal conditions are at level 4 of material, which is CBH, MgELH, and at level 2 of catalyst and BF5, which have the lowest value of SN ratio. However, material way more influential compared to the catalyst to change on decomposition temperature. This is due to the greatest delta gap shown in table 3.2.2. Based on the optimum features of material and catalyst, the optimum decomposition is CBH MgELH on decomposition temperature. Okay, as can be seen in figure 3.2.1, CBH MgELH serve as a material and NBF5 serve as a catalyst that correspond to the lowest SN ratio and lowest decomposition temperature with the gradient of the material and catalyst that shows the difference in height reaction response. The material and catalyst discrepancy shows the differential values that lead to the decomposition temperature value. The value for the material decreased when the level increased from the first level until the fourth level, while the value for the catalyst decreased for the first and second level, but then increased again for the third and fourth level. Under the optimal conditions, for the material, CBH MgELH gives a very large differences in order to get the lowest decomposition temperature, while for the catalyst, NBF5 catalyst give large differences in order to get the lowest decomposition temperature. For that reason, the optimum value on decomposition temperature is at 330 degrees Celsius based on the optimum value of material and catalyst.
Okay, now we proceed to the larger the better SN ratio and optimal condition analysis for hydrogen release. As you can see here in this slide, it consists of two tables, which is table 3.3.1 confirmation test at optimum condition on hydrogen release, and table 3.3.2, which is response table for signal to noise ratio on hydrogen release. In this investigation, the larger the better is chosen since the highest hydrogen is always desirable. The largest SN ratio corresponds to the optimum characteristics. As you can see in the table 3.3.2, it summarizes control factors and their catalysts of level 4, which is non-catalyst, and the material of level 1, which is CBH. Among these control factors, catalyst is more influential factor affecting the response due to the largest difference in delta in the table 3.3.2. This is because change in catalyst will affect the result of hydrogen release. As you can see here in the table 3.3.1 confirmation test at optimum condition on hydrogen release, we highlight the system for the number 4, which is CBH, and the catalyst is non-catalyst for the highest hydrogen release, which is 9.6. And for table 3.3.2, we highlight the highest material, which is level 1, 18.14, which is CBH, and for the catalyst, we highlight the level 4, the highest catalyst, is 18.45, which is non-catalyst. From the table, we highlight that in this investigation, the larger the better is chosen since the highest hydrogen release is always desirable. The largest SN ratio corresponds to the optimum characteristics. Optimum conditions are the catalyst of level 4, which is non-catalyst, and the system level of 1, which is CBH. Catalyst is the most influential factor affecting the response due to the largest difference in the delta, which is in the table 3.3.2. Okay, this is figure 3.3.1, which is main effects plot or data means for SN ratio. Therefore, in figure 3.1.1, the optimum condition for the material and catalyst are CBH and non-catalyst, which contributes to the optimum hydrogen release, which is 9.6. As you can see here, the highest system is CBH for the SN ratio, for the catalyst is non-catalyst.
Hi and Assalamualaikum. My name is SHARIFAH binti ABDULLAH. I will proceed the presentation about result and discussion of smaller the better, SN ratio and optimum condition analysis on activation energy. Table 3.4.1 Confirmation test at optimum condition on activation energy. In this table, there are 16 values of activation energy. For the control factor, there are two control factors, which are material and catalyst. Material have 4 levels, which are level 1 CBH, level 2 CBH and AALH, level 3 CBH MGH, and level 4 CBH MgALH. For the catalyst, there are also 4 levels, which are level 1 TIF3, level 2 NBF5, level 3 TICL3, and level 4 none. Based on the result from table 3.4.2, which is response for SN ratios on activation energy, it is shown that the optimum conditions are from level 2 material, which is CBH and AALH, and a level 4 catalyst, which is none because of the lowest value of SN ratio. The catalyst is more influential factor compared to the material, which is affecting the response of activation energy. This is due to the great difference in delta shown in table 3.4.2, which is 4.71. Activation energy result depend on the changes of catalyst and use of the catalyst. Therefore, based on the optimum condition for material and catalyst, the optimum activation energy is 88. Next is the figure 3.4.1 main effects plot for SN ratios. There are two control factors here, which is materials and catalysts. For material, CBH have the highest value of SN ratio. From CBH, the SN ratio decreased to the lowest value at level 2, which is CBH and ALH. SN ratio keep increasing to level 3 and level 4, which are CBH MGH and CBH MgALH. For catalyst, start from level 1 catalyst, which is TIF3. The SN ratio increased to the highest point, which is level 2 catalyst and BF5. From the highest point, the SN ratio value keep decreasing to level 3 and level 4 catalyst, which are TICL3 and non-catalyst. As you can see, as there is no catalyst used, it leads to the lowest SN ratio and lowest activation energy. For the conclusion, in the study of hydrogen storage properties and catalytic mechanism of magnesium hydride plus calcium borohydride composite for hydrogen energy was done using Taguchi method by applying the smaller the better and the larger the better criteria. There are two parameters as a factor, which are material and catalyst. Based on ANOVA, the system and catalysts are insignificant for decomposition, temperature and activation energy, but significant for hydrogen release. Based on the SN ratio, the optimum value of decomposition temperature is material level 4, which is CBH-MgAlH, and catalyst level 2 and BF5, since it has the lowest SN ratio. Material at level 1, CBH, and catalyst level 4, which is none, is the optimum value for hydrogen release because the SN ratio has the highest response. And for the activation energy, the optimum value is from catalyst level 4, which is no catalyst added, and the material level 3, which is CBH-MgAlH, to lower the response of SN ratio. That's all from our group. Thank you.